Taking 7 check.
Hello, sir. Good afternoon. Am I audible? Yes. So let me begin. So good afternoon, everyone. So today I'd be taking through a small journey on understanding the tropical circulation with moist static energy. So here I'll be taking you through 4 papers. That is one by Ham et al. In 2007. Then 3 other papers by Fan and Dominguez in 2021, 23, and 24. So these are 20 years apart. So basically the papers all use how one energy budget explains the tropical circulation, its future weakening, and the errors that are seen in climate models. So I'm Shankar Ram. I'm a PhD ERP student at IISc from ISRO. So at the outline, I would like to highlight that we are going to go through this whole topic in 3 parts. First would be some slides, that is 5 slides on the physics we need. Then in that, I will be looking at what the tropical circulation is. Then one number that quantifies the whole thing, that is omega. Then we look at what moist static energy is. And then the energy budget of a column of air. Then next, we'll propose to look at what stability is and how energy rising in a column carries this energy away, and then some equations. These are the basic physics we need. Next, we will be looking at each of these papers one by one. So first I'll look at Ham et al. 2007, where they solve the El Nino puzzle, which I'll be talking about with the energy budget. Then in 2021, Fan and Dominguez come up with something called the MSEB. That is one equation that diagnoses the whole tropical circulation. Then we look at their work in 2023, where they look at why warming slows the circulation. And finally, I look quickly through the models and how they get the circulation wrong, why that happens. And basically, the answer to all this also will be explained. Finally, I will be looking at what we learned from the whole approach. So the tropics are, to the first order, a giant set of overturning cells. Over the warmest pool, moist air first rises and the water vapor condenses and it rains. And then the ascending branch, all this is constrained. And then the outflow happens at the top and then it comes back over cooler regions and that will be sinking air. So the sinking air is drier and cloud free. So this is why a large part of the subtropical deserts sit where they sit because they are all regions of sinking air. This is all what we know. So now we compress this whole picture into one field, that is omega. Omega is the vertical velocity, vertical pressure velocity. And in this paper, we will be interchangingly using omega and omega 500 because the papers really look at the notation slightly differently. So because pressure decreases upward, a negative omega would mean rising air, and rising air means raining. And a positive omega, as the opposite would be, it will be sinking, and that means it is dry. So every map I will be showing today will be a map of omega. And this question of what is this omega depending on and what sets it is what the whole theme of the understanding of these this session would be. So moving on, the first basics, the background is the energy budget of a column of air. So the central quantity in our analysis is MSE, that is moist static energy, which is defined as CPT plus GZ plus LQ. So CP is basically the specific heat at constant pressure. Temperature is T, G is the acceleration due to gravity, Z is the height above the reference level, and L is the latent heat of vaporization, and Q is the specific humidity. So this basically is a term which encompasses three parts, that is the heat, the height, and the moisture into one thing itself. So it is basically nearly conserved as the air parcel rises, and it is very easy to keep track of this, and it is very clean for accounting the total energy of the air parcel. So when you look at a particular column of the atmosphere, so this will be the surface, this is the top of the atmosphere. So at the top, the energy comes in, and that could be the net energy flux due to solar shortwave, shortwave, and then the outward long wave infrared. Over here also we'll have similar solar insolation and the outward long wave from the radiation from the earth. Now, other than this, there is also an entry point that is due to advection. So winds blow in moist or dry air, and so that will be moist, warm or cold air into the column, and this is called advection. And all this, so when advection happens, moist or warm or moist air comes, the energy of the column increases, and cold and dry air, the energy decreases. So a column in surplus energy must rise, and a column with deficit energy must sink. So this is what the whole premise is. Now, first we'll look at another aspect, that is the definitions which is given in the paper. So we are using Fan and Domingue 2021's paper, where they provide basically one idea of the moist static energy profile. So this is how it varies with temperature and height. So just looking at one particular stretch vertically, we see that the moist static energy is higher here, then it reduces, then again lower, higher. So that is over here. And this blue dot is the basic height of the tropopause. This is the moist static energy profile. Now, on the C, what we see is a deep, something called the baroclinic mode. So this is basically the vertical shape of tropical vertical motion. So there is inflow at low levels, fast rising at around 400 HPA, and then outflow near the top. So this is the dominant shape of the tropical circulation, and this is called the first baroclinic mode. Now, now let's look at the equations for this. So MSC, as I just mentioned, is CP plus GZ plus LQ. Now, from the first principles, we have the balance of QDiv, that is the total energy flux in the column, as the sum of the three terms of advection of moist static energy, that is the vertical integral from surface to top of the atmosphere for the zonal component, meridional component, and the vertical component. So this can be rearranged, and that will give us the vertical component of the moist static energy integral as the difference between the energy available minus that of due to advection. So the vertical movement basically requires energy, and a part of this energy which is given to it, that is the net radiative input, is lost due to horizontal advection of moist static energy. So this is one way to look at it. Hence, whatever vertical motion is will be can be defined in this way. And a column, basically a column's energy budget can be understood through this term. And now this can be further simplified, and then one way we can try to quantify it is using the omega max term. So omega max can be just obtained by this, and this denominator is something we call the GMSB. We'll be talking about gross moist stability with the baroclinic mode in some time. But what we understand is GMSB, if it is positive, then omega max's sign is completely dependent on the numerator. So that is, if the sign of omega max is dependent on the sign of the energy available in the numerator, plus the surplus means it will rise and deficient means it will sink. So this already is covered. Now let's look at the next set of equations. So basically, now looking at the equations that I developed in the Fan and Dominguez paper, I'll be looking at the simplest equations. So starting from Neal and Held in 1987, which they proposed the gross moist stability idea, they have utilized this and then rewrote it in this form. That is omega 500 is basically minus G by GMSB brackets advection plus F net. So this is basically this equation itself. This equation itself written more simply, that is advection term and the F net term divided by the GMSB. Now GMSB is basically the gross moist stability weighted by the first paraclinic mode. So you remember this figure. So here is the vertical MSE profile. And now we basically weight the MSE change with this gross moist stability. And that is what we get as the GMSB. So, so the capital M is the gross moist stability defined nearly by Nealon and Held. And that is basically a vertical integral again from surface to top of the tropopause. So now we assume that the GMSB is greater, the paper assumes that GMSB is greater than 0. And so the sign of omega is the sign of the energy available. So that is all the physics we require. Now let's look at one paper at a time. So in 2007, Ham et al. Tried to understand the interesting puzzle of the El Nino. That is, usually when you have a SST, which is neatly and uniformly present during an El Nino, we usually assume that the rainfall should also be neatly and uniformly present. But no, the air sinks over the still warm Western Pacific. That is, even though there is differences in temperature, there is some areas where the air still sinks. So to understand this, what they did is they traced the energy budget and they found out that it is cold, dry subtropical air that advex into the column that causes the descent. And when there is descent, there is no rain over there. So to prove this, they also did some modeling and using a switching off advection, and that removes the sinking. So this is the overall picture. So I'll just look at it in detail. So this looks, let's look at this puzzle visually. The top panel shows the equator during an El Nino mature phase. That is, this dashed line is the SST. So we see this is around the date line. And we see that it is nearly flat from 150 east past the date line and again to 150 west. So around it is equally warm on both sides, about 30 degrees. And this solid line, which I am tracing here, is omega. That is inverted sign. That is, if it is positive, it is rising ascent, and it is negative, it is less, it is decreasing. So basically, what happens is there is the difference. That is, if SST were the only thing which controls omega, basically this should not be the case. It should be a clear follow track, but that is not what happens. So there is a peak of the rising motion at around 170 west, and the air sinks over the Western Pacific where the water is still warm. So this is on the bottom is the spatial view of this. So we clearly see the SST, which is uniformly spread from this area. So during during El Nino, omega decouples from the SST. So something else other than the sea surface is steering the Walker circulation. So this paper basically talks about that. So to diagnose this, basically we try to look at each component individually. So on top, the top two panels are the climatological values, and the bottom two are the El Ninos. So we see that if you a dotted line, that is the F net, it alone isn't able to show what is happening. But when we look at the El Nino, we see that there is a strong peak near 170 and a strong dip over here near the date line. So this straight line, the black line is basically the meridional advection, and this is strongly negative nearly the date line. So looking at the initial equation, we have energy available F net, then we have the zonal and meridional component. So if you look at the zonal component, it is relatively flat, so that can be ignored. So all the part which is remaining is the meridional component. So the q div minus meridional component is actually the energy available for vertical motion. And if we look at the rightmost image, top bottom right D, we see that it is exactly mapping each other. That is flux plus advection. That is the numerator together track the observed omega. Omega is the dotted line. So this is what we understand from the energetics. Now the question is, what causes this advection? What is the whole idea? Like, we clearly say that this is happening. Now, what causes the advection? So now is where we look at the causal mechanism. So it could be where do these draining winds come from is the first question. And is this mechanism causal? So earlier we see that it could either be that because there is upward movement, that is why the uh, advection happens, or the vice versa. So we have to understand this. So for this, the paper, the work they do is basically they use a linearized GCM and they try to reproduce the result. So basically what they do is they take the linearized GCM and they initialize it with a standard heating in the Central Pacific near the date line. So what they observe is they get the classic Rossby wave response. So basically on this figure, this is the control experiment where they heat the Central Pacific. This is the date line we see here, and then they heat the Central Pacific, and they get the Rossby wave response. So here there will be two cyclones developing, and that is what advects the moisture, the cold, dry air into the equator. So to test this using our equation, they basically use a control experiment where they flatten the T and Q gradients. So what happens when T and Q gradients flatten? That is, even though there is U and V, the dm by dx and dm by dy become zero. So that is, if we basically try to remove this component from the Q div, the numerator. So what happens when that happens? So this is the basic omega structure, and we see that there is the the asymmetry which we see here disappears. So here we have the rising air and here we have the sinking air. That is no longer present in the control. So switching off the advection, the West Pacific sinking disappears. So we can say that the mechanism is causal and not just correlation. So the basic idea is using this simple equation of the MSc budget, we are able to identify what is happening in the El Nino's puzzle. So the next paper which we look at is the first paper by Fan and Dominguez in 2021. So here is where they try to introduce a tool called the MSEB. So they basically have the problem they try to solve is the energy budget was well and understood by this Ham et al. For one particular situation. Now what they want to do is they try to diagnose the whole tropical circulation. Can the mean state, seasons, El Nino, everything be modeled by this? So what they did is they built an MSCB tool to model omega with the same F top plus H surface plus advection by GMS. They followed Neal and Hell's principle and tested it against ERA5 and CMIP6 models. So the MSCB model, in short, is this is a picture from the paper itself. So here they took at two particular things. The top row is basically the numerator, and the bottom row is the case when the denominator. So we'll look at the picture in detail. So the top row basically has the same column in three different situations where the net energy surplus is happening and there is a balance in the energy. So energy is coming in from the top over here, advection over here, and leaving at the bottom. And here it is equal coming in and going out. And then here it is a deficit in energy. So what happens? We get an ascent here. There is no motion in the center and then a descent here. And that is a sinking happens. So the bottom row, same energy input, but it is different. The stability of the atmosphere is different. Stability of the column is different. So now let's look at what happens when the column is more unstable, that is more stable, more unstable, that is less stable, it will rise farther, and less unstable, it is the rising is lesser. So we try to look at the MSCB model using this equation again. I'm just rephrasing it so that it is clear. And we try to explain what happens in circulation and various aspects of it. So does this work? They are somehow able to create this plot. So this basically shows how omega 500 varies over the month, mean monthly time series at the central equatorial Pacific from 3.75 north to 3.75 south, from 150 east to 150 west. So in this particular area, they are able to average and get out omega profile and use the MSCB model, and then they are actually able to track this extremely well. So this is able to reproduce it perfectly, and this basically shows how well the MSCB model is able to show the variability. It is not just the mean circulation which is able to capture, it is also able to capture the variability. So now let's look at the third paper. That is the second paper by Fan and Dominguez, where they look at climate change. So climate change models have long projected that the planet would warm, and the overturning tropical circulation would be slowing. And that will be around 10 to 15% is how much the circulation will weaken by 2100. So Held and Soden in 2006 also say that it must weaken. And in their paper, they say that rainfall increases by 2% per degree and moisture increases by 7%. That is the Clausius-Capron equation. And finally, so they say that the rainfall is roughly circulation times the moisture. So circulation has to change, but they do not tell why. All the models till now have shown that some due to circulation must change due to some weakening regionally, or it is model dependent or basically incomplete. So Fan and Dominguez, what they tried to do is they ran the MSCB model on this, used 31 CMIP6 models, and varied one budget at a time, and they found the answer. So this is an interesting way to do this. So basically what they do is they swap one term at a time. That is, uh, they keep the historical data of CMIP6 from 1970 to 1999 as HIS, and SSP5 of 8.5 warming from 2070 to 2099 as the future scenario. They use our well-known equation and basically compute omega with the every term in the RHS as set to HIS value. So basically we get a baseline. So what they do is they take every single term and put the HIS value and get the HIS omega. Now, to find out what causes some effect, they swap it one at a time. So one at a time, they swap it to the SSP value and keep the remaining other terms at HIS value itself. So, and then what they do is they subtract the new hybrid omega minus the HIS baseline, and then they term it the term sensitivity contribution. So from the CMIP6 models on the right, we have a figure where they show the RMS ratio, and we see that CMIP6 models all show a weakening from 10 to 15%. So all these dots you see here are various CMIP6 runs. And MSCB model is also able to somehow get this exactly. Now our idea is, why does this happen? So now they basically divide this into three components, that is FNet, advection, and GMS. FNet, advection, and GMS. So they try to swap each part of the with the SSP values, holding others at HIS. So FNet, when they swap it, they see a strengthening. That is, it is positive. It is nearly 5. Advection also, it strengthens. And only GMSB, when they swap, only then do we see a weakening, and that to around 20%. So actually we see a 10 to 15% weakening. So only GMS is what actually weakens it. So now GMSB is your culprit. Now we go ahead further and try to understand what in the GMS is causing the weakening. So GMS is basically M divided weighted by the baroclinic mode. So we swap again. So GMS is divided into baroclinic mode and MSE gradient. So we swap the uh, only the baroclinic mode, circulation weakens by around 26%, as you see here. And then we swap only the MSE vertical gradient, and we see that circulation actually strengthens. So this again is wrong, and this will be our answer. So now, why does this omega shift upwards with warming? So that again, they look at it in two particular ways. That is the temperature profile change or the tropical height. That is P underscore T. That is PT is the height at which the pressure of the tropopause. Now, to understand this again, we have an equation for omega, the baroclinic mode, and then they swap the values again, like holding the pressure tropopause height fixed. They try to see, and we see that the temperature profile really does not really change anything. But when they hold the temperature profile fixed, use the SSP values, the baroclinic mode actually shifts up, and that strengthens at levels comparable to this. So now we see that this is how they explain that baroclinic mode is what causes the tropopause height is what controls the whole thing. So to understand that, they have provided some figures. So the blue line is the historical line and the red line is the SSP. We clearly see that at the top, the SSP's tropopause height is at a,
Can you pause for a moment, please?
yes.
The network here is interrupted.
Okay.
You may continue, Shankar.
Yes. So from the previous slide, we saw that it is omega is actually due to the height of the tropopause, and that can be actually seen from the data itself. And tropopause is actually higher in the future scenarios. This is the time series of the pressure of the tropopause. So tropopause is originally at around 98, and then it reduces up and it decreases to around 80. So that the tropopause height is actually seen to reduce by 15 to 20 HPA by 2100. And that, if you look at the current scenario using CMIP6 models historical simulation and future minus historical, we see that it is happening across the tropics, and that is clearly explained using our particular equation. So this equation has this power to explain even this particular aspect of pointing out what causes the ozonic circulation to change. Now, when we look at the whole mechanism, the authors have basically divided it into four basic steps. First step is they say that CO2 forcing lifts up the tropopause. Step two is because of this lift, the baroclinic mode shifts upward. And step three is now stable upper troposphere. So the effective stability of every tropical column increases. And step four, since there is the tropopause is at a higher level, the circulation stretches up and becomes weaker. So that is all seen. So Held and Sodden just showed that circulation must slow. But here we show that what exactly happens, and warming makes the atmosphere taller, and the taller atmosphere overturns more slowly. So the final paper which we look at is the same model applied to various model biases. That is why climate models get tropical circulations wrong. So when we look at the rainfall of the world in CMIP6 models, we see a lot of errors like double ITCZ, the cold tongue, the Atlantic, the position of the Atlantic rainfall slightly lower. Then the Indian Ocean dipole is also somewhat wrong. So which physical errors actually cause these biases is what they try to look at. For this, what they did is they looked at six boxes you see here, two around the Indian Ocean dipole, then three in the Pacific and one in the Atlantic. So for the double ITCZ index, they use these three Pacific boxes. They basically take north plus south minus the equator, and that is one. Next, the Atlantic the cold tongue is basically using the same equator box. that Atlantic bias is one box and the Indian Ocean dipole is the difference between these two boxes, east minus west. So the clever thing they do here is they're basically showing the omega profile here again. They try to apply MSEB to the error, that is CMIP model minus ERA5 data, and they compare it with the coupled model and the AMIP models. So what they try to show here is a little complicated, but I'll just try to explain. So since we have the equation again, the three components, that is FNet, then the advection and the GMS, they use each term's contribution and show it in different forms, different bar charts. So the first one is the solid is the CMIP model, then the dotted is the AMIP model. So they try to kind of model each and every every component of this, and finally they attribute it to different ways in which the boxes behave. And finally, they say that it is basically the atmosphere flux errors, that is FNet, which is causing this, and it is amplified by the oceans. So this is how the whole work carries out in various. The Nealon and Held started all this. Then Ham et al. Came in, and then they used this model first by using solving the El Nino Walker anomaly. Then Fan and Dominguez used three ways. They introduced the MSV model and tried to use this equation in powerful ways. So basically, the uh, idea is this is all very simple, transparent, and attribution is very easy to do. But the thing is, it is just a diagnostic model and not a forecasting model. And from what we understood is, even in their paper, they say that it is weaker over land and at low levels. So it works basically over oceans. And this equation which they use, that is QDiv, is the sum of the three advection terms, does have noise in our analysis. And they really say that it is very less in the paper, and they move on with it. And this noise comes not just from the residue term, but also basically the residue term because of the conversion from the sigma coordinate to the pressure coordinate. So all these models use the sigma coordinate, but when we use the data, we all give it in pressure coordinate. So over land, we try to do something. We use the MSC budget for various components, the U, V, and omega part, and we tried to understand it, and we found that the vertical component of the MSC budget is very small over land. So this is the comparison between land and ocean. So we did our own comparison with over India in this range from 70 to 90 and 10 to 30, and BOB from 80 to 100 and 10 to 22.5. And we see that there is a total difference between what we get. So over land, this is a really tricky situation, and over ocean, this model performs better. Now at our end also, we try to reproduce the omega profile, omega time series using the DSE budget, and we were also able to basically use a similar equation and try to predict the omega 500 from the ERA5 data using this simple model. So this is our result, and finally we would like to say that it is just a diagnostic model and works on large scales, a monthly and approximated over large regions. So that is all from my side. Thank you so much. So are there any questions?
Yeah, I think Oishi Chakravarti has a question. You can ask directly.
Hello, am I audible?
Yes, ma'am. Please tell me.
Yes. Oh, okay. So I just had a question about the first paraclinic mode that you showed. I just wanted to ask, Because from what I see in this paper, they show that the baroclinic mode is top heavy. So I want to try to understand where is this calculated over? So is it calculated over entire tropical oceans or some particular box? Because I'm curious about what this baroclinic mode would look like over regions like the East Pacific, where the circulation is known to be bottom heavy.
Yeah, so basically, when we investigated this paper further, they use this baroclinic mode as a smooth curve. And this, in the paper, they say that it is for across the whole tropics. But in our understanding, in our analysis also, it is we do not really get a clean, smooth curve like this. As you said, various regions would have various profiles for the baroclinic mode.
I just have a follow-up question to that. So in that case, if this analysis were to be done in instead of across the entire ocean, just on regional, say a box over West Pacific or a box over East Pacific, would the results be different? I mean, I just want your opinion on it.
Yes, so mostly over the oceans, I think the results should more or less be the same, like similar at least. But over land, the paper themselves, they show that it is not very true. So if you say that it is some area in the Pacific, I think results should be more or less similar. But I'm not very sure. I would have to look and let get back to you.
Okay, thank you.
I have a question that this in that equation which you have shown, their omega 5, they have approximated it to omega 500. So why is it particularly to that level? Because on the right hand side you have the entire moist static energy vertical integral, so which is generally dominated by the upper level. So why is it omega 500 they have approximated? Is there any answer for that?
So I don't really know, but what I think is omega 500 is just to know the maximum. Like they assume that it is the maximum. So they try to see the sign of omega. It is rising or going down. So maybe that is a reason.
Okay. Any other questions? Okay, thank you. Yeah. Yeah, they can directly, yeah.
Only do that?
No.
Yeah, okay. Yeah, so this year's monsoon is going through a very interesting phase now. Last week we discussed how yeah, we can, yeah. Yeah. So last week we saw that there was a rapid decline in rainfall due to a break situation. But this week it has recovered rapidly so that sorry, this point is almost now close to normal. Okay, this is remarkable. Okay, in 1 week time, things recovered, and that's most clearly seen in the next figure. You remember we discussed a lot about this decline from 60 millimeter per day to 0, but it has come back to the same value, even higher. Okay, so the very rapid decline of the break and active, and so the question now is, what is causing this? Remember, last week we discussed it is the dry air at 7 millibar coming in, okay, based on T. N. Krishnamurthy's paper. Now the question is, what has happened to that? Okay. So I wanted to, this is the core monsoon zone, not everything up to today. Okay. Now it's funny, IMD puts out the first data around 2:30 for the core monsoon zone. But for all India, they'll do it after 3 hours. I can't help it. So core monsoon zone, given the latest data, see the 22nd July is gone in above what it was there. Okay. And if you look at the standardized background, it was weak for so many days, 10 days, then now become very strong. Okay. So if this continues, then it may turn out that this year July may be close to normal, which will be remarkable. We are thinking of 2002, but that's not happening. Okay. Now, yesterday, rainfall data, I want to show you how widespread it is. This is the calculation of IMD of all stations, rainfall of above 100 millimeter per day, which is very high rainfall. Okay. Look at it covers all the Gujarat, Uttar Pradesh, Himalaya, everything. Of course, Jammu and Kashmir is on a flood. So the point is that this heavy rainfall is not just one part of India, it's widespread. Okay. Now let's look at yesterday's rainfall. You can see it's fairly widespread from Jammu and Kashmir all across India, except South India. We were in trouble. But if you look at the average, 1st July 21st, the previous week, which we discussed, is pretty bad. Okay. So this previous week, this is impact of last one day, they're not right comparison, but showing it was in a deep break phase, but it recovered in a matter of one day. Okay. Now, if you look at the cumulative, you can see still huge portions of India are, actually half of India is doing badly. Okay. For half are normal and few are excess. Now, let's look at how the Mithuna model of, how many of you know Mithuna is the name of the month from 15 June, 15 July, and how they named it. So it's all onset phase of the monsoon. Okay. So that one correctly reproduces this U-shaped curve. Okay. Numbers are wrong, we saw that, but the active break cycle they're getting correctly. On the other hand, okay, last 5 days they got it right more or less. Okay. But this one is off. This is also off. It's something like that. But the slope is right. On the other hand, TFS data completely wrong. TFS data predicted an absolute drought. Okay. So the question is why? So to me, the situation is to do with how the wind is coming into North India. Now, if you recall, we discussed this. First, I'll show you the 10th of July, when the winds are coming, as always, from Pakistan all the way to into Japan. This was the break phase. Now, 21st, 10 days later, it is coming down to Arabian Sea, then turning into, there's a lot of rain in the coastal regions of Karnataka and Maharashtra, okay? But here it's not happening. Here the attraction of dry air has stopped. So that is the change that has occurred. But what surprised me when I looked up the climatology, this is the climatology. Okay, it surprised me. So what's happening is you can see that this is the geopotential height around the Gulf. There's almost a valley through which wind comes, but it is coming directly to Delhi. It goes down, and I believe it is picks up moisture as it comes into South India. Okay? And this is you're going to see what's going to happen today, what's happening, prediction. It comes all the way here, goes down, and then turns around and goes up, which is amazing. Okay. So this part, of course, no, the trough here, of course, it will go around, but the high wind speeds come from Central Asia all the way down, go past essentially Maharashtra, and then turn around and then go up. Okay. Now, this is for 21st, and that is for this outdoor forecast. I'm sorry. Yeah, two different items. Sorry. This is 850 millibar, which is what normally you look at. See the difference. At 850, you don't get this. Okay? Because there are mountains there in Afghanistan and they block it. Okay? So this 100 millibar is unique because of all the mountain range. So air is able to come all the way from circulation around here. Here it doesn't. Okay, now this is the for tomorrow, day after tomorrow, how it is going to go. Well, now let's look at ECMWF forecast for the next, let's see. Anyway, for the, sorry, this I should go back. Yeah, first I'll show this. 20th to next week, okay? This week and next week, still will rain over the Indo-Gangetic plain, but the week after, things start breaking up, okay? You can see this below normal here, and this is isolated to west and east, okay? Now, next, after that is this one, third to, sorry, yeah, yeah. And this is third to 10th. Still something is there, but below normal rainfall is in the heart of monsoon zone. Now we come to next 2 days, next 2 weeks, 20 to 27. I'm sorry, getting it all wrong. Okay. Yeah, 17 to 24, all negative. 24 to 30, all negative. Okay. So this forecast of, if you believe it, then August is not going to be good. July may turn out to be normal, but August is below normal. Remember, June was below normal, so it is not going to be a good monsoon here if August stays. So we will watch it because I'm not sure about the last 2 weeks because all these forecasts are good for the first 2 weeks. Next 2 weeks are not sure, so we'll keep this in mind and see what happens next few weeks. And they go to, I'm sorry. Yeah. Now, what is happening to MGO? MGO is still around here, the same reason. Okay? So those of you who believe that MGO is there, it affects the monsoon to take it back because it's not happening this year. Okay? MGO is still there in the same phase, but monsoon is changing a lot. So there are local factors. Then let's look at the SSG anomaly a week back. So my feeling is that not only this playing a role, this is also playing a role, which I them showed for June, July, some years back. And there's also a hint of something happening here, which I'll talk about a little later. What happened in Atlantic, which Bohi pointed out to me. Now, let's look at the comparison between I think July of these two. You can see there are very different steps. Okay? In this period, till 28 July, the forecast of Mithuna is above and IMD is low. We hope this is true. If this is true, then July rainfall will be almost normal. Okay. Now, what the prediction from GFS and the Open Center? There's a huge difference here. Here they are saying Pakistan is under essentially weak and drought, and this is saying this is very interesting because a 2 week forecast generally they should agree. So this is surprising. So next week we will see what's happening there. Now, this is the part Mohit pointed out. There is a development of a negative SH anomaly, here, in the coast of Africa. Okay? This is called the Atlantic Nino. We discussed this last 2 years. Okay? So an Atlantic Nino is positive, it has one impact. Now it's negative. Okay? Now you can see that there again. Sure. So I'm saying this will play a role, this will play a role, this also has some role to play. Now this is the close-up of that. You can see clearly a lot of upwelling there and cold water coming here. Okay. Now this is a paper we discussed by Ramesh Kumar Yadav. There's been many papers on this. The first year of SSJ year, which was very high, 50% that is dominant phase. When this happened, he claimed this is what happens over India. Okay, anomaly. Now it's not very clear. If this is positive, then will increase of South India, Indo-Gangetic plain, and it will be there over Central India. Okay. Now this is opposite, negative. So according to him, this will have an impact of reducing rainfall here, increasing rainfall here, increasing here. Partly, he is right, but remember that this anomaly is not very strong. This is from minus 0.5 to 1. So I'm not sure it's going to overcome the effect of 3.4. There's some effect, but not much. So this is closer to the same thing, that's all. Yeah, after he removes 3.4. He does think, he looks at how things are with 3.4 removed, still there is some thing in there. But remember, it's not the significance is a very small region, so I don't trust it so much. Now let's look at the coming week. According to Mithuna, it's going to be above normal. So let's assume it's around 9 millimeters per day for the next 9 days. Okay, so there's under 80 millimeters. So we'll come close to 270 to 80 for the month of June, which is quite good if it happens. Okay, so we'll see. Now let's go back to the each of the long-term forecast. In June, they said July will be below normal. In July, they said above normal. So in reality, I think it will come close to normal. So it will be the mean of these two. They made a prediction of a drought here and a flood here, almost 1 sigma. So the reality is in between. Look at August. In June, they said it's below normal. August is further below normal. Of course, September is the worst. We discussed that. So we believe that these 2 months are going to be below normal. Now, you look at CFS V2 forecast. Not only below normal or India, entire region, the entire Indonesian maritime continent, India will be below normal. And this is essentially the large scale east-west anomalies you're seeing there. Okay? But if you remove, this prediction looks back to India, but you'll be careful. All these models, their forecast over land is not good. So if you take this and ask which are the significant things India doesn't count. You take the yeah. You look at the significant data here. All over oceans. So this is well known. All climate models, couple models do well over oceans, do well over land. So this is the old result for a long time. And this is confirmed here that all the significant changes are here, but not over land. Okay. There's no land region where you can see significance. Even Africa is well. And this is for September, equally bad. Okay. So CFS V2 agrees with ECMWF. Now let's look at models. Of course, this we have seen before. August looks pretty bad. This looks good. But if you look at NCAR, it's 50-50. Okay. So let's hope this is true because this looks more favorable to India. Now this is multi-model mean, which is a combination of CFS V2 and NCAR, so some little impact over Orissa. Now, if you look at all our anomalies in the last 1 month, you see a clear pattern that's there in CFS V2, all the way here, descent, and here is ascent. So this is the classic east-west surfacing change, not just equator, entire region. Now, this comes out in the velocity potential very clearly. There's an outflow from the Pacific Ocean and inflow at the upper level over India and the maritime continent. So these are consistent. Now, I want to add with a interesting quote from Neil Shubin, who is the new president of the National Academy of Sciences. Okay. Now, he has got a tough task. He's dealing with a crazy president who's cutting all the funds for science. But I admire his optimism. He's an amazing person. Read his books. He's written really nice books. He is talking about two things. One, that science is one of the greatest human created. True. And computer will not change that. What it is saying is that although AI and ML may take over most people, but the truly creative people, no computer can match. If Einstein or Feynman or somebody, no computer can come to that. Okay, that's the point. The second part, very interesting, that science communication difficult in an era where social media is there. You are being given all kinds of wrong information, and it's a very tough challenge to tell people that, for example, climate change is going to be happening. Okay, I'll stop here. Are there any questions? Yeah.
I'm just curious why climate model is better prediction of precipitation.
Huh?
Why climate models perform better over ocean than
There's no simple answer. All I want to argue is that the ocean is somewhat easier to predict because if you look at the presentation by Shankar, for the ocean, there's a lot of energy always coming from below, evaporation, guaranteed. Land is very difficult. Land only sources out there. There's no source below. Okay? And so land is and land has a low heat capacity. So the weather fluctuates. Oceans are very steady. That's the big reason. But big point. But what? What? Pretty size of this much faster. Okay. Okay.
the last sentence what is there? Doesn't goes to existing in direction. But social media seems to reinforce the existing belief.
Yeah.
But existing beliefs they motivate in the most positive direction. And why
Okay. The next meeting is not a meeting. Janani, it's here. Yeah. So what I talk about? Okay. Good. Thank you.